I welcome everyone to our little workshop. Just a few words before I start. We come from Subotica, a little town on the north of Serbia, and we do software development for embedded systems. So this subject of this workshop is embedded Linux device drivers. I will keep or give a short introduction. I will keep it short because we would like you to have the more hands-on experience than the long talk. So about the embedded systems, what is most characteristic about an embedded system? It's its dedicated function. So by definition, embedded system is a system which is a part of a larger system with one dedicated specialized function. It's usually based on microcontrollers. Microcontrollers are basically CPUs which differ to standard general purpose GPUs because they usually have, or they always have, onboard memory and peripheral controllers. One more thing which is important from the standpoint of the microcontrollers is the optimization. That means that a microcontroller is usually highly optimized for a special task. For example, there are digital audio processor, DSPs. Another thing about the microcontrollers today, there is a variety of applications, basically from applications in consumer electronics to industrial applications. Then there is healthcare applications, military, and so on. From the hardware standpoint, as I already mentioned, the specific thing is that the peripherals are on chip. You have all the needed peripherals on your microcontroller. Many CPU architectures are produced. So, for example, MIPS, some proprietary or RISC architecture. However, today the most popular architecture is ARM, by far. From the standpoint of the word length, they are usually from 8 to 32 bits, but today, for example, the ARM processors are available in 64 bits as well. Another great thing about this platform is that there is a lot of cheap development boards, so anyone can start working with them. For example, the Arduino, which you already probably know. Another important term is SoC, system on a chip. This is basically a highly integrated microcontroller which consists usually of more than one microcontroller. You have one sort of a general microcontroller and, for example, a hardware decoder and a set of other chips which do, for example, digital audio processing and so on. So, from the standpoint of peripherals, there is really almost anything that you could imagine, from serial communications interfaces to synchronous serial communication. Then there are the universal serial bus controllers, network interfaces, field buses. These are mostly characteristic for industrial applications. Then timers and discrete input-output, general-purpose input-output, and analog to digital or digital to analog converters. So this is the typical hardware which you will find on one microcontroller. Not all, but let's say a combination of these. So about embedded Linux. It's similar to the microcontroller. It's purpose-built. So we optimize it for the application which we need it for. By definition, it consists of a kernel and the minimal user space. The minimal user space might be made usually with the build root, or it might be embedded into the kernel itself. It's the so-called init RAM FS. From the standpoint of the device drivers, which are our topic today, you can see that the device driver actually provides a connection between the physical device and the user space. So that's the role of the driver. From the standpoint of Linux, Linux creates a variety of classes of devices. There are network devices, storage devices, USB devices, and so on. Typical operations when you want to write a driver is memory mapping, often interrupt handling, and application of various time routines, for example, application of high-resolution timers, and so on. And since our topic is, or our subject is a workshop, I would like to give the word to my colleague Andrija, who will now proceed with the actual workshop. But in the meantime, before we switch, you can find all the sources for our workshop on these URLs.
My name is Andrija Prcic. I will do the practical demonstration of this hardware. So first of all, this presentation and the practical example is based upon build root. So in order to build this, you actually just do a git clone of the repository. You run a few simple commands. So first of all, make Raspberry Pi dev config. So this is the default config for the Raspberry Pi. The build root includes this. It will make a configuration file for this. You can run make nconfig to adapt this if you want, and then run make. So it will actually build everything at that point. So it will download absolutely everything that it needs. So starting from a compiler for your host computer to the Linux kernel sources and everything that you have selected for the target platform. And of course, depending on your hardware, this can take from maybe 15 minutes to over an hour. Okay, questions or not really questions now? Okay, no presentation at the moment. So, practical part. Okay, so I have turned it on and it's booting. I have already built the entire build root and copied it to an SD card, and it's on the Raspberry Pi. So this is the system booting. And your login prompt looks like this. And well, basically it's a very minimal system. Okay, and okay, so I have prepared a few examples. Should have opened most of them. Okay. Okay. So the most basic example, so this is a Linux driver. The first thing a Linux driver needs is an init function and an exit function. So you define these. They have some predefined template. You can name it as you want. You use this module init macro to actually define for your module what is the init function. And this module doesn't really do much. It's basically the most basic GPIO module that you can have. So when the module initializes, and here, it will write out hello, and then it will iterate through this array that I have defined. So these pin numbers are actually from the datasheet of the hardware, and I have connected my LEDs directly to these GPIOs. So it's not random, you have to know your hardware, what to actually do. So you need, of course, to do some includes and basically iterate over everything, request the GPIOs that you want to use, configure it as an output direction, and give it a value 1. So it will go to high voltage. This is 3.3 volts in this case. And of course, the return function the init function has to return. For the exit function, similar thing is done, but in this case, it will actually, so it will again configure the output direction of the GPIO, and it will give a value of 0, so it will turn off. So it doesn't really do much, but this is something that you start to build from. And I have already, in this case, so just everything that you see here is available already on the GitHub, so you can just clone it, and you can just run a simple make command. It will build. You have a few files. The most important is this one that ends with .ko. So that's a kernel object or a module, a loadable module. So going back to our Raspberry Pi, I can log in here. I have already pre-built and copied all the modules here, so we can save some time. And I can, in smod, insert module, this first example, and it will say hello. And if you look around here, you can actually see some GPIOs light up, here as in down here. And if I remove the module name is actually Raspberry GPIO, but I have just renamed the files for when loading I can distinguish which version I want to load. And when I remove it, it will say bye, and it will turn off the GPIOs. So simple. So, you know, there's no dark voodoo magic in writing a driver. It can actually start very simple. So for the next example, this one actually starts also from the init function, but apart from outputs, you can also have inputs. So inputs are usually buttons or switches or something similar. And of course, just like you request the usage of GPIO pins for output, and you said, I want this one to be an output, in the same manner you do, again, a request for a GPIO, and you say, I want this to be an input. And one more thing, so this example does is it initializes a timer called a blink timer, which would obviously do some blinking. And so this is defined here as a global structure. So this, you initialize this timer, you say it has a function, then when a timeout occurs, this function will be called, and we actually start the timer. So this kTimeSet is a function which converts normal time to jiffys, which are internal to the kernel timing mechanism. So this will do 1 second and 0 nanoseconds. And of course, so when the timer triggers, it will call this function. And in here, I have defined a static variable which would change each time. So I negate it. And for these outputs, I do some modulo. Odd and even numbered pins would have different outputs. And I also read out the input pins. So I can do a get value of an input pin and print this to the debug terminal. So to show this, so this would be this one. And now it's doing blinking. And it's, as I have said, it's showing the input values. So it has 2 input pins defined, and they are both at a high level. This is because how the hardware is connected. I have connected the buttons to short the input pin to the ground when it's pushed. So I'll demonstrate that. I put this, one of these down to 0. Now the other one. And now both. Okay, so this method of reading out inputs at predefined time intervals is called polling, but it's not really a great idea because for fast signals, or if somebody is bored, you can actually push and release the button before the timer triggers, and this is something you would not catch because at the both times you read this, it will be in the high value. So you can miss some signals, and this is where interrupts come in. An interrupt is sort of a signal in the processor when something changes. And you can, for all of these GPIOs, so I will unload this to stop it. Okay, so the next one is interrupts. So similar thing for the timer, so I have left this in, but I have also done, so for these input pins, I have requested the GPIO, but I can also request an interrupt. IRQ is interrupt request. So I convert this GPIO number to an interrupt and do some more flags. So I want to be notified when this signal is rising and when this signal is falling. So when it changes from 0 to 1 and from 1 to 0. So in both of these cases, I will get this function called with my GPIO, well, actually with the interrupt number, and then I convert that. So other than that, this example does basically the same thing. So it's, again, when it's unloaded, it will turn on, turn off everything, and it still has that timer. So this is the example number 3. Okay, so again, it's blinking, it's polling, but when I also touch the button, it will show up immediately that a signal has been requested. I'll just show this. Okay, so as you can see, it's still polling, it's still reading, but even in the middle, if something changes, it will notify right away. So basically, that trigger, the interrupt handler function is called, this one. I get the interrupt number, which I convert to a GPIO number, and then I read out that value, and I print that to the terminal. So as you have already seen on the example. So it's nothing really complicated, but it's very useful that you don't really have to ask. So if you're doing communication to a hardware chip, you don't really have to bother that chip with, are you ready? Are you ready? Are you ready? Are you ready? No, it will notify you when it's ready. You know, at that moment, the chip will change its output level and actually do something like pushing a button, and you get this interrupt. And when you get this interrupt, you can actually ask that chip exactly, hey, what's up? What do you want to tell me? And then it will say, okay, I have some data ready for you, or there's something wrong, or something, whatever. But you don't really have to constantly ask, and it's really bad practice to constantly pull signals and ask, hey, are you ready? Are you ready? Are you ready? Okay, so going on. Okay, so we have a timer which blinks, but wouldn't it be nice to actually be able to turn that off or on demand? So this is what the next example does. So the initializing functions has grown quite a lot. So for this, first you need to register a device class. So your device driver needs to belong somewhere, and that somewhere would end up in here. So you in sys class, you have different classes for device drivers. And inside of those, you would then have various drivers and components. So first we need to make a class where this driver would belong. And of course, I have picked an appropriate name, Balcon 2014. Hello, okay. So the next thing is to register a character device. Well, character devices are some legacy, well, not really legacy, but the first type of drivers that ever were made. So basically they emulate a serial input and output with a file. So you have a virtual file which has some read and write handlers defined, and you can write something to that file, and this would be written to your hardware or memory buffer or something like that. And again, when you read something, it would go in the other direction. But this will be handled in the next example, but for the starters, you need to actually have an object in kernel space which would have some other structures defined with it. So first you need to define one of these character devices. Okay, so you create a class, you register a character device, you create that device, so you can actually have something in dev whatever, and that file would be registered and created automatically. And then with this you can actually, well, apart from that, you would also have, well, actually I can load the module and show it. So in this class, I have now Balcon 2014. And in here, I have a Raspberry GPIO example, as I have defined this for this device name. And this thing has, so some of these are default, so you can have this dev file, which actually gives you a major and minor number for the Linux kernel drivers. So every character device in, so I have now also created this file, and so you also have the same major number and minor number in here. So a system like UDEV or something like that that handles this device tree can create and remove these as needed. But in any case, so you need also, so in here, this class, so our class, our driver, you also can get this directory, and with it you can do whatever you want. So what I wanted to do is create this blink control, and to do this I actually had to define a read function for this file and a write function for this file. So basically the read function just checks whether the timer is active, prints that as an integer, as in 0 or 1, and that's it. The write function would read out what was given in this buffer written from the user, convert that to an integer, and then check, do you want to turn it on or off? So if you want to turn it on and it was not active, then actually do the start of the timer. If it was already active, then just write out some informational message. And in the same manner, if you want to turn it off, check whether it was already off, and then just don't do anything. So I can actually write something to this, and timer is not active, it was starting. And I can now turn it off, and it will start blinking. So it's quite simple. So you actually have to define a few functions like this. You define this attribute with a macro, call it blink, say what are the permissions on it. So I want this to be read and write for absolutely everybody who has access to this computer. So it's readable by the user group others, writable by the user group others. You name the functions, and then this attribute is put inside of an array, and that is put inside a group. So yeah, it's kind of a lot of containers and layers, but for this, then you just say create a sysfs group with this object that I have registered here, so this device file, the character device file, that group, and of course, if there's some error, return back. And of course, if you are unloading the module, then you have to actually remove that as well. So basically, whatever you have created when the module is unloaded, destroy it. Otherwise, you can be left with a whole lot of crap. And the fifth example actually uses that character device. So one very nice example of a character device is a 7-segment display, which you can see on the board. And it's actually going to print out some numbers, well, the number sequence. And if you actually see the display, it has done that. Okay, so this file actually has some function, so I can do something, write something to it. And of course, this is some garbage that will be output, and it will do some alien language signals. But this is also not really difficult to connect. So, hello. Okay, so you have to define a file operation structure for this character device. Then you have defined write, open, and release. Well, of course, reading from a 7-segment display is not really a useful thing to do, but I have put in a prototype just in case you want it. So when you open it, when you actually want to write something to that file, first you open it, then you call the write function, then you close it in the end. So you have to define all three, not just the write functions. Okay, so you open the device, there's a mutex, so for mutually exclusive access, so no two processes can write at the same time to that character device. So if the mutex is unavailable, then say this device is busy and just abort. And otherwise the mutex will be locked and you have access and you can actually call the write functions. The write function doesn't really do much. It just does, again, GPIO output. For I have defined for this 7-segment display for each segment 1 GPIO. And it's in this array, so each bit has whatever I have. So since characters are 8-bit values, what I write to this character device, I have just did a bit mask and shifting, and basically 1 bit is written to 1 segment. So if you do know how it's arranged, you can actually write a number sequence or some signals that you want. So this function gets called and it actually configures the GPIOs. You can see the output, and this is, well, basically how you communicate with very basic hardware. This is how you actually communicate with even advanced hardware. In some cases, you do bit masking, you do GPIO input-output. But of course, if you want some high speed, you use already predefined protocols like I2C, SPI, or something like that. You can bit bank most of them, so you can actually do fine-tuning. Well, you can match bit masks and do a clock output on 1 pin, and then signal output on all other, and achieve some results, but it will be slow. So if you want to communicate with a proper hardware chip, then use some better signal. But for the sake of this introductory example, this is basically what I have wanted to show you. So now we go back to the presentation and the question slides. So any questions? Okay, shoot.
Today, are the researchers interested in reverse engineering drivers, or all the manufacturers are willing to give that step?
Datasheets are something really very painful to obtain. For some reason, it's like top secret military achievement or something. I don't really know why. So if you want to write your own custom-made hardware and drivers for that, pick a manufacturer that actually cooperates and gives datasheets with the chip. Otherwise, you will have a headache. I mean, sometimes even if you do get a datasheet, it will not be complete. It will lack some information, or it will be the wording can be also quite confusing, and you don't know that for some things to do, you have to previously do some other thing and initialize things differently if you want to run in that other mode or something like that. So yeah, if you reverse engineering is doable, but takes too much time and it's maybe not worth the effort. Any other questions? I'll take that as a no. So thank you for your time and your attention.